Let's continue our discussion of estimating causal effect. And in this lecture, we'll introduce the concept of control variables. Let's do a little review. In week 12, we started the discussion of estimating the causal linear model with one causal variable x. So there is only one parameter that we want to estimate, that is the causal effect of x on y. In this causal linear model, the arrow term u summarizes the factors other than x that participate in the generation of y. So because u has economic meaning, the factors in u are real world variables, and in practice, they may or may not be uncorrelated with x. So that means OLS regression of y on x may or may not give us consistent estimator for beta 1. We did talk about one setting where the OLS estimator of y on x will give us a consistent estimator, and that setting is the randomized control trial, in which x is randomly assigned in a way that is not correlated with any of the factors in U. And if randomized control trial assumption is satisfied, EXU equals 0, so that means x and the arrow term are orthogonal, and OLS regression of y on x will give us a consistent estimator for the causal effect beta 1. On the other hand, in a randomized control trial, if we also have some other pre-treatment variables collected for the individual, say W, if W is also available, we discussed in the last video that we can choose to use these W's in the OLS regression as additional explanatory variables. And we showed that using these additional covariates will still give us a consistent estimator. And in fact, in general, it gives us a more accurate estimator of beta 1. Today, we'll go into a different setting because our random assignment assumption on X is clearly too strong. In a lot of data set, even in some of the randomized control trial data set, the random assignment assumption for X does not hold. For example, I'm sorry. So when X is not randomly assigned, it may be correlated with the error term. Just to give you a very simple example, suppose that U contains the intelligence of people and X is the education, then intelligence clearly is correlated with education. When X and U are correlated, when X is not randomly assigned, but instead is correlated with the factors in the error term, we say that X is endogenous, and the word endogenous means generated within, which means X is generated at least partly from the factors in a model that also generates Y. So for example, education is a result of intelligence, just in the same way that income is also a result of the intelligence. So when X and U are correlated, we say X is endogenous. So what do we do when X is endogenous? We first show that OLS regression of Y on X will not give us a consistent estimator for the causal effect when X is endogenous. So that's the consequence of endogeneity. Suppose X is endogenous, that is, it's correlated with the error term U. Then when you project U on X, you are not going to get a constant, but instead you're going to get a non-trivial function of X. So when you project U on X, you're going to get alpha 0 plus alpha 1 times x, where alpha 1 is not 0 whenever x is correlated with u. If the projection of u given on x is this linear function of x, then the projection of y given x will be the following, because y equals beta 0 plus beta 1x plus u. And that projection will be equal to beta 0 plus beta 1x plus projection of u given x. So we did exactly the same derivation in the previous video. And now, because projection of u given x now is no longer a constant, but instead is a linear function of x, we can write that linear function here. Now collect terms, get beta 0 plus alpha 0 plus beta 1 plus alpha 1x. So the projection of y on x is this linear function of x, where the projection coefficient of x is beta 1 plus alpha 1. So as you can see now, this projection model relating y and x and the causal model relating y and x now deviate from each other. We know the OLS consistently estimate the projection model. Okay, so the projection model and the causal model deviate. So this is the causal model. These two now deviate. They have different coefficients, different intercept, different slope coefficient. And the slope coefficient is what we focus on. Now these two models deviate. If you run OLS regression of y on x, the OLS estimator for the coefficient on x, so the beta 1 hat, what does it converge to in probability? From previous lectures, we know OLS always estimate the projection model consistently. It doesn't always estimate the causal model consistently, but it does always estimate the projection model consistently. So therefore, the OLS coefficient on x will converge in probability not to beta 1, but to beta 1 plus alpha 1, the x coefficient in the projection model. So the OLS coefficient on x converges in probability to beta 1 plus alpha 1, and that is not the causal effect of beta 1, right? So that is not equal to the causal effect. So endogeneity cause the OLS estimator to be inconsistent. However, we say that all is not lost. We can still save the situation if we can restore random assignment by controlling some covariates W. So what do we mean by that? So we want to find a vector of covariates W such that conditional on W, X is independent of the error term U. And when that happens, we say this W is a vector of control variables. That's controlling W, fixing the value of W. Okay. Varying X is independent of varying U. If that happens, if that is the case, we say X is conditionally randomly assigned a given W. Or in other words, X is conditionally exogenous given W. So exogenous is opposite to endogenous. So when such W vectors exist, we say X is conditionally exogenous given W. And this conditional random assignment will help us to consistently estimate the causal effect of X, that is beta 1. So when is conditional random assignment plausible? In fact, in some randomized control trials, not the experimenter may not just randomly assign the treatment to the whole population, but instead the experimenter may first divide the sample into several groups and then divide the sample into groups according to observable random vector W, and then randomize the treatment X within each group. So this is reasonable when the groups are not even. Kind of, you have a majority group that is the majority of the population, and a minority group, which is a small proportion of the population. If you just randomly divide your sample into treated sample and untreated sample, it is possible that your treatment is not given to many of the people in a minority group. And if that happens, then your data will not be very informative about what the effect of the treatment is for the minority group, right? So therefore, to circumvent this kind of problem, some of the experimenters would divide the sample first into groups according to the observable random vector W, let's say minority or majority group, and then randomize the treatment within each group. Okay, so give 10% of the majority treatment and maybe give 20% of the treatment to the minority group. So in this kind of RCTs, X is not completely randomly assigned. X is related to the W, right? X is related to the W, and if W is correlated with some of the factors contributing to Y, then X would be endogenous in that sense. However, conditional on W, within each group defined by the value of W, X is randomly assigned. So conditional random assignment is reasonable in such a situation, even though the unconditional random assignment is not reasonable. So that's one setting where conditional random assignment is a reasonable assumption. Another setting is a non-experimental data. And this is actually where control variable approach is used most often. In non-experimental data, sometimes it is possible to argue to tell a story about how X is generated. Sometimes it's plausible to argue that X is a result of a mechanism that depends on some other observables, W, and a purely random noise. So so you can now, in this non-experimental data, it might be reasonable to tell a story about X, where X is a result of W and some noise that is completely random, not correlated with anything, any observable or any of the unobservables in you. If that is the case, then we can also reasonably believe given W, X is randomly assigned, because given W, what's left varying in X is this purely random noise that's not correlated with you. Now, I will give you two examples later on, but for now, let's see how conditional random assignment helps us to estimate the causal effect of beta 1. First, let's understand precisely what conditional random assignment means. In the strong form, conditional random assignments means conditional on W X and U are independent, meaning that conditional on W, the joint PDF of X and U can be written as the product of the marginal conditional distributions, right? So conditional on W, the joint distribution of X and U equals the product of the conditional density of X and the conditional density of U, both given W. So now if you ignore the W here, that is just independence, right? That is just independence between X and U. But with the W, this is the conditional independence between X and U. So this is the strong form of conditional random assignment. So given W, among population with the same value of W, say among majorities, X and U are not dependent. Okay. So that is the strong form of conditional random assignment. And there is another way to write this, which is the conditional distribution of U given X and W equals the conditional distribution of U given only W. Okay, so that is X can drop out of this conditional, drop out of this conditioning set. Okay, so these two statements are equivalent. You can derive one from another using conditional density formula. So, and the conditional density formula is the following. So, so this is, so to derive that, we can write this as FU XW divided by FXW. XW equals FUW UW divided by FW W. All right, so now in order to go from there to this first line, we're gonna divide both sides by FW W and multiply both sides by FXW XW. Okay. Once I do that, the left-hand side will be exactly FXU given W, XU given W, and the right-hand side will be two ratios. One ratio is the joint density of U and W divided by marginal density of W, and the other is joint density of XW divided by marginal density of W. And both are conditional densities given W's. And that is exactly this first definition. Okay, so these are the two expressions for conditional, for the strong form of conditional random assignment. And this strong form of conditional random assignment implies the weaker form of conditional random assignment. That's conditional mean of U given X and W equals conditional mean of U given only W. That is, once U conditional on W, X no longer matters for the mean of U. Okay. Now we're going to use this weaker form of the conditional random assignment to derive a conditional mean model from the causal model. Recall that we want to estimate beta 1 from this causal model. Now we want to derive a conditional mean model from it. Now take a conditional expectation given both x and w on both sides. So we're going to get conditional expectation of y given x and w equals conditional expectation of beta 0 plus beta 1x plus u given x w. Now expectation of sum equals sum of expectation. So that equals expectation of beta 0 given x and w. But beta 0 is a constant, so beta 0 can be taken out. And beta 1x can also be taken out because once you are given the value of x and w, beta 1x is also given. It becomes a constant. So that can also come out of this conditional expectation. What cannot come out is u. So eu given x and w will have to be still here. But now we're going to use the conditional random assignment assumption. Conditional random assignment implies that conditional on w, x no longer matters for you. So therefore, x can drop out of this conditioning set. So now we have written ey given xw as a linear function of x plus a possibly nonlinear function of w. So x no longer appears here, but this is still a function of w. Okay, so we got this. So that is eu given w. So we have written ey given x and w as this function of x, linear function of x, plus a possibly nonlinear function of w. Now for simplicity, let's assume this possibly nonlinear function is not nonlinear. Just for simplicity, further assume that this function is a linear function of w. Make this linearity assumption now. Then we have a conditional mean model, a linear conditional mean model relating y to x and w, right? If this linearity assumption is true, then we know this conditional mean model is also the projection model. And the OLS regression of y on x and w will consistently estimate beta 1. Okay. It will also consistently estimate the gamma 1, but gamma 1 is not a coefficient of interest to us at this point. So this is a linear conditional mean model if the linearity assumption that we just imposed about EU given W is correct. If that linearity assumption is correct, this is a correctly specified conditional mean model, and it is also a projection model, and therefore OLS regression of y on x and w will consistently estimate beta 1. Okay. So now we see how we can use the control variable that makes x satisfy the conditional random assignment assumption to consistently estimate beta 1. Right? So if given w, x is randomly assigned, and if EU given w is linear, then OLS regression of y on x, and the control variables will give us a consistent estimator of the causal effect. So notice that we have two ifs. One if is the conditional random assignment. One if is the conditional random assignment that is conditional on W. X no longer matters for U. And the second if is the linearity of this function. Okay, linearity of the conditional expectation of U given W. We say that this first assumption, conditional random assignment assumption, is the key that that makes this thing work. So that's the key assumption that we're not gonna relax in this context. Well, on the other hand, the linearity assumption can be greatly relaxed. This can be greatly relaxed because you have the freedom to add nonlinear terms of W and interactions among the W terms without fundamentally changing our technique, right? Without changing even our argument to argument for the consistency of the estimator of the causal effect. So this can be relaxed by adding nonlinear terms of W and interactions of terms among W's. In practice, what do we do in practice? When you have a control variable, you don't know whether it should be controlled linearly or non-linearly. You can try different specifications. Just maybe you can try a sequence of specifications. One is more flexible than the other. And then you check how sensitive your estimator for beta 1 is. So hopefully, once you add enough flexibility, enough nonlinear terms and interactions among the W's, your estimator for beta 1 become more or less stable. It's no longer changed that much when you add even more nonlinear terms. And that's a good point to stop adding more nonlinear terms. All right, so now there is one hidden assumption in here that we haven't discussed. The hidden assumption is hidden in the no perfect multicollinearity assumption for this conditional mean model. That is, there should be no perfect linear relationship between x and the control variable. If there is, then clearly this OLS regression of y on x and w will not be possible, and our ability to estimate beta 1 consistently is also sabotaged. So so what that means is if we use a linear specification for EU given W, if we make W enter linearly, then this condition means W should not be able to perfectly linearly predict predict X. And if more flexible specifications is used, say if you're also using W squared or W1 times W2 and W2 squared and so on, then the no perfect multicollinearity condition requires that X cannot be perfectly predicted by those more flexible forms of W either. However, the control variables can be correlated with X. It cannot be perfectly correlated with X, but they can be correlated with X. And in fact, the control variables are almost always correlated with X. All right, so that's a theory for how conditional random assignment assumption helps us to estimate the treatment effect of X. And in the next video segment, we'll introduce two examples